So vector semantics are actually the embeddings that are popularly or most probably used with the help of neural networks, and the first model that was proposed in vector semantics was word2vec, and word2vec was proposed by Mikolov and his colleagues. And another kind of embedding that is again somewhat better and improved version of word2vec, not the version but similar to word2vec, is glove embeddings that was given by Pennington along with Manning. Manning is again a senior scientist in Stanford, and Mikolov works at Google. So we will see again word2vec with the help of some examples. Now word2vec is very popular because it is very simple. Its structure is very simple and it is very fast to train, and they have made the code available, and we use just the classification settings rather than simple probabilistic approach. So the classification settings involves the learning of a classifier and predict some class. So instead of predicting that class, we are just concerned with the weights of that classifier. So earlier we studied the point-wise mutual information and the vectors generated with the help of that. So that was purely probabilistic and there was no learning involved. It was a purely count-based method. That means it used to count the number of words and its context present in a corpus, and then apply some probabilistic methodology using the joint probability and the conditional probability. So this is a little bit different from that because we involve the learning here, and we obtain much powerful embeddings than the PPMI version. So instead of counting how often each word W occurs near a word apricot, we would like to actually train a classifier whether a word W is likely to show up near apricot or it is not. Like it's kind of a binary classifier that we will train whether a word W is near the word apricot or it is not near to it. So we are not actually concerned about the prediction outcome, but we are concerned about the weights which we will be using them as embeddings. So let me again remind you that embedding is another term for vectors. It is same as word vectors, but popularly they are called as embeddings, and when these embeddings are learned with the help of neural networks, they are generally called as embeddings. Right, so the word2vec applies a technique that is called as negative skipgram with negative sampling. And what is this negative and positive sampling? So we assume that a word is connected or is in the neighbor of another word, then it is a positive sample, otherwise it is a negative sample. So positive samples can be very easily derived from a corpus. Suppose there is a target word T and there is a context word C. So the words that are appearing as neighbors of each other will be termed as positive examples, and the words that are not appearing as neighbors but present in the corpus, they will be considered as the negative samples, right? And then we can use a logistic regression classifier or any other kind of classifier. So in case of word2vec, the Mikolov had used the neural networks. They have used shallow neural network in order to train a classifier, but for simplicity we will be using the logistic regression classifier in order to train the weights. So what is skipgram? Skipgram means that we have a target word and we assume that the context word is around the target word present as its neighbors. So if we have a window of plus minus 2, that means we will consider the two words to the left of the target and two words to the right of the target. So if this is an example, I would like to go to some place nearby for lunch. So if we consider the go as target word, then within the window of plus minus 2, like to someplace nearby, these are the four words. Like to is towards the two words left to the target word, and someplace nearby is the two words right to the target word. So these four words can be considered as neighbors or specifically as contents. So go, like, go to, go someplace, go nearby, these four tuples are generated with the help of positive sampling. So these four tuples will be considered as positive samples. So similarly, we can generate a lot of negative samples. We can randomly choose some words from the corpus and then make the tuples with those. So go aardvark, go incubate, go 12, go therefore may be considered as negative samples, and these aardvark, incubate, 12 and therefore are randomly selected words from the corpus that are not the context of the target word. So initially what we have is that we assume that each of these tuples, as they are directly proportional to the similarity, so these tuples cannot be converted into numerical form. So in order to convert them into numerical form, we replace these tuples with their similarity. So we need to calculate for each of these tuples. There will be a dot product. Again, the dot product will be in the form of a vector. So the dot product of go with like, the dot product of go with 2, the dot product of go with someplace. Similarly for the negative samples, we will have the dot product of all these. So go and like, all these individual words and context will be initially assumed as a vector of random real values. Like, so go will be a vector of some random values, like will be a vector of some random values. Similarly aardvark will be a vector of some random values, and each vector will be of fixed size. So we can make an assumption that let us represent each words as vectors of some length, say suppose 300 or 100 or 500, which is randomly initialized, right? So now we will replace the tuple of word context pair with their vectors, and in order to replace them with the vectors, we apply the similarity. So we get two kinds of probabilities that will be generated. One is the p positive given that tuple, and one is the p negative, that is fake, given that tuple. So in order to use that this t comma c, the tuple, as some numeric value, we will replace it with the dot product of their vectors, and these vectors have been randomly initialized for each of the words present in the corpus. So we can replace the tuple with the similarity, right? But similarity is, again, it cannot be used inside this formula p of positive given the tuple or the negative given the tuple, because we need to have some, this p of real given c is actually the p of real divided by p of t comma c. So this t comma c should be again a probability. In order to convert this t comma c into the probability, we first convert t comma c into the similarity of t comma c, and then we convert it into a score between 0 and 1 with the help of the logistic regression sigmoid function. So p of positive given c becomes equal to 1 upon 1 plus e to the power minus similarity of t comma c, and p of negative given c will be equal to 1 minus p of negative given c. Since it is a binary classifier, it will be equal to 1 minus p of positive given t comma c, and when we evaluate this, we see that it is equal to e to the power of minus of similarity of t comma c divided by 1 plus e to the power negative similarity t comma c, right? So we replace now this similarity as the dot product. So what is the dot product? It becomes as, so it becomes as 1 upon 1 plus e to the power minus of, so this is t1 dot multiplied by c1 plus t2 multiplied by c2 plus t3 multiplied by c3 plus dot 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 tv multiplied by cv. So we have v vocabulary size here. Sorry, it is not v, it is actually d. So d is the dimension of the vector. So we have two vectors. One vector is the term for term t, and one vector is for the term c. So we have these two vectors. So we randomly initialize these vectors. We have randomly initialized them. So we randomly initialize means that we give some values like t1, t2, t3, t4 and so on up to d, where d is the dimension. D is the dimension of vector. Similarly, we can have this as c1, c2, c3, c4 dot 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 cd. So this is the vector t, and this is the vector c, right? So when we multiply each of these individual scalar components, we get the dot product. So vector t dot vector c is actually equal to t1 dot c1 plus t2 dot c2 plus t3 dot c3 dot 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 td dot cd, right? So we get these scalar values, right, as parameters of this probabilistic model. Similarly, we can write these vectors for all the negative samples, so this and all the positive samples. Then we generate the loss function. What is the loss function here? So this is the loss function for, we need to maximize the positive samples. That means we need to maximize the probability that the positive samples must have the higher probability and the negative samples must have the lower probability. So with the help of this loss function as a function of, so this loss function L is a function of t1 I comma t2, this is t1 I is the ith word. So instead of writing like that, let me write it like this: t11 comma t12 comma t13 dot 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 td1 dot 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 tdn comma c11 comma c12 comma c13 dot 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 cd1 dot 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 cdn. So this is a loss function of these parameters, right? So t11, this is the dimension and this is the word position or word of the corpus. So this is actually the ith word of the corpus. I must write, this is ith word of corpus. So in this way we have this loss function in the form of, so when we will expand these all the probabilities will be in the form of these t11, t12 and so on. And so we will expand this and then we will apply the stochastic gradient descent So this stochastic gradient descent is an optimizer that will optimize these parameters. So we will get the optimized value of all these parameters, then we will put up again these optimized value of these parameters in the same function. We will get the function that will be treated as a classifier, right? So we can use a simple gradient descent or stochastic gradient descent, and these are the settings. This is the word, this is the context. So again, the target word is of d dimensions, and v is the vocabulary, v is the number of words. So here, instead of using d n, I must use v here. So this is v here, so tdv. So these are actually the number of parameters that will be present. The number of parameters with the help of a word is mod of d multiplied by mod of v. Similarly, for the context we have mod of d multiplied by mod of v. So the total number of parameters that needs to be trained is equal to mod of d square dot mod of v square, right? So we can train these parameters with the help of neural network, with the help of any classification algorithm. So in order to simplify, we are using the kind of logistic regression settings. Otherwise we could use the neural network settings, so which is quite similar. Instead of using the logistic function here, we may use some little different settings. Like we have this initial input layer, we have this hidden layer, and we have this output layer. So this input layer, these are the pairs or tuples, and these are also the pairs, right? And these pairs are sampled with positive negative like this. So in this way we can also learn a neural network. And when we obtain the hidden layer, this hidden layer, so the weights of the hidden layer may be treated as the embeddings, right? So this is a kind of a neural network which is actually of this form. We have high dimensions, we have v number of word pair, and v d cross v number of word pair tuples present here. We reduce it to the lower dimension, and then we again reduce it back to a higher dimension. So this kind of neural network was actually trained by the Mikolov. So this is of dimension, so say 300 or 100 or 500, right? So we don't require any dimensionality reduction algorithm here. It directly reduces, the neural network directly reduces it into the 300, 100 or 500 dimensions, right? So this kind of autoencoder neural network was used by the Mikolov. Okay, so that's all about the summary of the word2vec. We can initialize with the 300 dimension vectors. We can use the logistic regression, and we can train it, and then we can just keep the parameters of the classifier and use them as embeddings. So these are some results put up by Mikolov, like if the target word is Redmond, so a nearest word with Redmond or its nearest context, maybe Redmond Wash dot, this is the short form of Washington, Redmond Washington, and like this. So similarly for graffiti, spray paint and graffiti and taggers, these may be the nearest to context words with the target word. Now what's significant with word embeddings is that we need to visualize them so that we are able to see its effect and realize it how actually they are working, right? So we have some algorithms for with the help of which we reduce the dimensions of 300 into 2 dimensions, right? So we have some algorithms like a principal component analysis. We have an algorithm that is the principal component analysis. That is PCA. We have the singular value decomposition. These are the two very popular algorithms for dimensionality reduction, SVD, and these work in similar manner. And we have another latest one, that is T of SNE, so which is very very powerful, and it actually converts n dimensions into 2 dimensions in a very efficient manner. So with the help of these dimensionality reduction algorithms, we are able to convert the 3 dimensions into 300 dimensions of the word embeddings into 2 dimensions. So that means we are having now 2 dimensions here, which is this is dimension 1, dimension 0 and dimension 1, right? So this is x-axis and this is y-axis. So each data point for a word which was consisting of 300 values, now it would, after reducing it, it would consist of only 2 values. So this vector, suppose a man, we have a word man and we got a vector trained for man. So this is of 300. So after applying the reduction algorithm, we get only 2 values. Now we can have these 2 values, we can plot it into on a 2-dimensional graph, or we can reduce it to 3 dimensions and we can plot it on a 3-dimensional 3 dimensions, and then we can study the visualization of the words, right? So we see here in this visualization the difference between man and woman, uncle and aunt, and king and queen. This difference between these 2 vectors, the vector of man, this is the vector of man, so the vector of man and the vector of woman. So this is the vector of man, so the difference of all such vectors is almost the same. Difference of uncle and aunt, difference of king and queen. Right, so we see that these blue arrows have almost the same difference, right? And similarly we can, so in this way we can analyze a lot of things. So we can analyze some kind of we can do gender analysis. So this is the gender analysis. So it is done by the people. So this is the brother and this is the sister, nephew, niece, uncle, aunt, woman. So this has been done on a lot of words, and we see the difference is almost the same here, right? Similarly, we can perform the analysis on comparative or superlative words. Comparative words. So we see again the vectors of these slow, slower, slowest, and short, shorter, shortest. These have almost the same characteristics, and right? So we can study these, and we can, with the help of the similarity and the differences, we can find out the vectors of other words that are not present in the corpus, right? So we can do all these studies. Some people have also studied the cultural bias problem that has been uh, present in the society. So they had studied the history documents, and they have studied the current documents. So these are William Hamilton and George Leskovec. They have done this study, and then they have seen the effect of what is the effect of words and their meanings changing throughout the history. So initially we see that the word gay was used some in some other meaning, and broadcast was used some other meaning, and awful is used with some other meaning in around 1850s, and then in 1900s they have been used with some other meanings, and in 1990s they have been used with some other meanings. So this study was done by them. Then there was another study that was done on the word terrific. So we see that there is a historical change in the meaning of sentiment of the word terrific. Initially from 1860 near somewhat 1860 to 1960s. So there have been, the terrific word have been used in the negative sense. It was termed as a negative sentiment word, but afterwards, after 1960s, it has been very used most commonly in terms of the positive sentiment, right? Similarly, these people have done another analysis on the gender bias and ethnic bias, and then they have showed that this is the graph representing women's occupation and women's bias, right? So the difference in women's occupation means that the difference between men and women. So they have taken on the x-axis, they have taken the difference between the occupation and women bias on the y-axis. So we see that the terms or the words that like nurse and housekeeper and librarian, these are more biased towards the woman, and the words like mechanic and carpenter and engineer, these are more biased to they are having actually low woman bias, right? So that means they are more towards the men bias. Similarly, they have done another analysis, that is they have taken year wise the woman bias, and then they have seen that for some period the woman bias is high in language, and for some years the woman language was low, and again for some years. So they have studied this woman bias with respect of the years, right? So this woman bias and also the average woman occupation difference. So women have been in occupation in around this, before this period and after this period, like this. So these kind of significant cultural analysis has been done by the people with the help of word vectors, right? So a lot of analysis have been done by the people. So these embeddings have been they have been really useful in different kind of linguistic and cultural studies.